Hello friends, welcome to engineering tutorial. So today we are going to resume our discussion on mechanics. So far in our discussion related to mechanics we have covered one-dimensional motion, okay, and we basically discussed the basic concepts related to one-dimensional motion, the three important equations of motion, the graphical analysis and some questions on it. So in this video and in the next series of video we'll be discussing motion in a plane. So basically it is two-dimensional motion. Okay, so first a quick review of some basic concepts, and it will be related to vectors. So I have already made a lot of videos related to the basic concepts related to vectors, which is in the basic physics playlist. So I request you to please watch all the videos related to that. If you have if you are new to the concept of vectors and if you have knowledge of vectors, then it's okay, you can proceed with this. But in this discussion there will be a lot of it is actually based on vectors, so it is necessary that you have a good understanding related to vectors. So if you want that, you can check the basic physics playlist where I have discussed everything related to the basic concepts, operations, properties of vectors. Okay, so first, in order to discuss motion, we have to first specify its position. Now, the position of an object or a body in space is specified by its coordinates. Its location is specified by its coordinates, where three important coordinates come into play: x, y and z on the coordinate axis. Now, in one-dimensional motion, what happened was that motion was restricted in one straight line. It was also called as rectilinear motion or straight line motion. So only one of the position coordinates it changed, while the other two it remained constant. For example, okay, let's say we have motion only in the x-axis, along the x-axis. So only the x coordinates they will change. Okay, the x coordinates that will change, while the y and z coordinates they will remain constant. Similarly, if motion happened only along the y-axis, okay, then the y coordinates they changed, but the x and z coordinates they remained constant. And similarly, if motion happened only along the z axis, okay, if motion happened only along the z axis, then the z coordinates they undergo change, while the x and y coordinates they remained constant. So that was one-dimensional motion, only one of the position coordinates that is undergoing change. Well, two-dimensional motion is two of the position coordinates will undergo change. Okay, so when two of the position coordinates are changing, let's say the x coordinate is changing and also the y coordinate is changing. Okay, it means, let's say initially let's say the particle is at here at the origin, and then it moved to this point. Okay, this is the origin and this is the, let's say this is the initial point and this is the final point. So both the y and the x coordinates they are undergoing change. Okay, both of them are undergoing change. So here the object is moving in two-dimensional motion because both the x and y coordinates, they are changing. Suppose the object then moved to this point, okay, this point. Let me by a solid line, let's say this, and again it moved to this point. Again the x and the y coordinates, they are undergoing change, okay, this. So again it moved, let's say, to this point. Again the x and y coordinates, they are undergoing change. So here if you see, the motion is restricted in one plane, which is the xy plane, because only the x and y coordinates, they are undergoing change, okay. So it is two-dimensional motion in the xy plane, or motion in the xy plane. That's why two-dimensional motion is also called as motion in a plane, okay. One-dimensional motion is motion in a straight line, okay. One-dimensional motion, as we all know, is motion along a straight line or rectilinear motion. Two-dimensional motion is motion in a plane, this, okay. Similarly, let's say we have another object which is initially in this position, okay, and then it moved to this position. Let's say it moved to this position. So here the x coordinate is changing, and along with that the z coordinate is also changing. Again it moved from this point to this point. So again x coordinate is changing and z coordinate is changing. Again it moved to this point, let's say. So again x coordinate and z coordinate. So here the motion is along the xz plane, because whenever the particle is moving or the object is moving, the x and z coordinates, they are undergoing change. Similarly, we can do the same thing for this, okay. Here let's say initially the particle is here and it moved to this point. So here the z and the y coordinates, they are changing. Again let's say it moved here. Again the z and the y coordinates, they are changing. So here the motion is along the yz plane, okay, yz plane, because only the y and z coordinates, they are changing. The x coordinate is constant. Here x and z coordinates are changing, the y is constant, okay. Here x is constant, and here in xy plane the x and y coordinates are changing, z is constant, okay. So this is motion in a plane. And in three-dimensional motion, what happens is that motion happens with the change in three of the coordinates, x, y and z, okay. So in order to visualize this, let's say this is the initial point, this is, let's say, x, this is y, and this is z. So let's say motion happened from this corner to this corner. I mean anywhere in between this line joining, anywhere in between this. Let's say the point is here. So here the x coordinate is changing, okay, the y coordinate is changing, and also the z coordinate is changing. It is very difficult to show the three-dimensional thing in a 2D picture, but here the corner to corner or vertex to vertex motion, this is three-dimensional motion. Or if the, let's say, the particle is anywhere inside here where all the x, y and z coordinates, all of them are changing, then that is three-dimensional motion. So more on that, now we are discussing two-dimensional motion, so let's not mix this. So just for basic understanding, here we have discussed that. Okay, so one-dimensional motion, two-dimensional motion, three-dimensional motion. Here we have discussed. Now is again, it's a review of the concepts related to vectors where I have explained in detail in the basic physics playlist. So here I will be not going into detail. Here I will be going in a quick way. So the concept of position vector. So the position vector is used to specify the location of a point, any point, with respect to the origin. Okay, it can be done for two-dimensional or motion in a plane, or location of a point in a plane, or location of a point in a three-dimensional space. So here we are discussing two-dimensional motion. So let's say we have a point P which is specified by the coordinates x, y. Okay, here the position vector, okay, that is specified as the x position coordinate followed by I cap, which is the unit vector along the x direction, plus the position coordinate y, the value of the position coordinate y, followed by the unit vector along the y direction. Okay, the horizontal and vertical axis. So let's say this position coordinate is, let's say it is 2 and 3. So the position vector OP vector, it will be written as 2i cap plus 3j cap. Okay, 2 is the value of the x position coordinate along the horizontal axis, x axis, and 3 is the y position coordinate, which is the position coordinate along the vertical y axis. Okay, 2i cap plus 3j cap. Now here if you see, this is position vector. Suppose we have any vector which is drawn by joining any 2 points. Okay, let's say we have an initial point I and a final point F, and we draw a vector with the point F, final point, as the head of the vector, and the point I, the initial point, which is the tail of the vector. We have discussed it. So initial point I is defined by the coordinates xi, yi, and final point is defined by the position coordinates xf, yf. So in order to express this vector joining the initial and final points, we write it as, let's say, if vector, okay, which is also called as displacement vector from initial point to final point. So it is expressed as the final x position coordinates minus the initial x position coordinates I cap, which is the unit vector along the x axis, plus the final y position coordinates minus the final the initial y position coordinates followed by j cap, which is the unit vector along the y axis. Okay, so basically displacement vector is the difference between the final position coordinates and the initial position coordinates for the respective components, the x component and the y component. So this is the x component and this is the y component, and we can always resolve any vector along the x axis and the y axis. It is called as resolution of a vector into its component form. So it makes the calculations easy, and in all of our discussions related to two-dimensional motion, we will be using this resolution of a vector. So always remember, if we have to represent a vector joining an initial point or starting point I, or any name you can give, let's say joining the tail and the head, the initial and the final point, the representation of the vector is always final minus initial position coordinates for the respective x and y. For x you will be using I cap, for y you will be using j cap. Okay, xf minus xi I cap plus yf minus yi j cap, where xi yi is the initial position coordinates, xf yf is the final position coordinates. Okay, so now let's say we analyze this whole thing. Let's say we have an object or a body which is moving along this curved path from this initial point to final point. So it has covered this distance by traveling in this direction along this curved path, but the net displacement is the straight line shortest distance joining I and F. Okay, this is the displacement which is represented here. This is the displacement vector, this is the curved path which represents the distance. Okay, the curved path, it represents distance, whereas the straight line path, the shortest path between these 2 points, that is the displacement or the displacement vector. So this is the initial point, this is the final point. It is happening along the xy plane, the motion. So now let us specify the coordinates. So here let's say the initial coordinates are xi, yi, and this is xf, yf. Okay, so this is xi and this is yi, and this is xf and this is yf. So delta x is nothing but the difference between the final position x position coordinates and the initial x position coordinate, and delta y is the final y position coordinates minus the initial y position coordinates. Okay, this much is clear. Now let us say we have to represent this displacement vector if. So here in terms of position vector we have to represent it like this. So here first we represent the position vector for the initial point y vector, which is the x component xi plus y component initial yi component yi, which is xi I cap plus yi j cap. That is the initial position vector. Final position vector, which is specified by the position coordinates xf yf, that is simply xf I cap plus yf j cap. That is the final point position vector. So the displacement vector if vector, that is final point minus initial point. So position vector of the final point minus position vector of the initial point. Okay, so this is the final point, this is the initial point. So final minus initial, which is represented as xf minus xi. Okay, xf minus xi I cap plus yf minus yi j cap. Okay, so this is the x component, this is the y component. Okay, or it can also be represented as the displacement vector delta r vector, which is equal to delta x I cap plus delta y j cap. So here delta x is change in x component and this is change in y component. Okay, so here don't get confused, here I have written xi minus 0 because the position vector of the origin, that is 0 I cap plus 0 j cap. Okay, so here if we have to specify the position vector of the initial point, so here it will be, this is the final, for this vector oi, this is the final point, this is the initial point, xi yi is the final point and 0 0 is the initial point. That's why xi minus 0 plus yi minus 0. Similarly, in order to specify the position vector OF vector, this xf yf, that is the final point, and O, that is the origin, that is the initial point. for OF vector. For each vector, the head that represents the final point and the tail that represents the initial point. Okay, similarly for IF vector, F, which is the head, that is the final point, that is XFYF, and I, which is the initial point, the tail, which is defined by the position coordinates XI, YI, that is the initial point. So that's why XF minus XI plus YF minus Y. Okay, so it's clear up to here. So we have defined the displacement vector. Now is velocity vector. So velocity, we know the basic definition which we have discussed in one-dimensional motion. Same here, change in position or displacement divided by the time interval. Okay. So if we have to specify here, as motion in a plane, vectors have come into play. So here velocity vector or average velocity vector. So that is again the displacement vector which we have specified here, delta r vector, which is equal to delta x I cap plus delta y j cap, which is this xf minus xi I cap plus yf minus yi j cap. That delta r vector by delta t, which is the time interval. Okay, so delta x I cap plus delta y j cap by delta t, which is equal to delta x by delta t I cap plus delta y by delta t j cap. So here delta x by delta t, which is change in position with respect to the x-axis divided by time interval, that gives us velocity along the x-axis. Okay, delta x by delta t, which is change in position along x-axis divided by time interval. So this is velocity along x-axis. Similarly here delta y by delta t, here it is change in position along y-axis with respect to time. So that gives us velocity of the object along y-axis. Okay, so as x-axis I cap, along y-axis j cap. So again the average velocity vector, it can again be resolved into two components. The x component, which is the velocity along the x-axis, the x component, and then the y component, which is the velocity along the y-axis. So here we have that. Okay, let's say this is the average velocity vector. Okay, it has the x component along the x-axis, okay, this x component, and the y component along the y-axis. Vxi cap, Vyj cap, and it is represented as this. So the average velocity is the magnitude of this vector, which is root over of Vx square plus Vy square, the sum of the square of the individual x and y components root over. Okay, another interesting thing, the average velocity vector is always directed in the same direction as the displacement vector. It means the average velocity vector, it will always be parallel to the displacement vector. Okay, so this is the average velocity vector. Next we have is the instantaneous velocity. So instantaneous velocity comes into play when we reduce this time interval delta t such that it approaches 0. We shrink the time interval. We have discussed it in detail in one-dimensional motion, the difference between average value and instantaneous value. Okay, so you can watch the previous videos related to one-dimensional motion for that. So here the instantaneous velocity vector will simply be the limit taken with delta t approaching 0, the time interval approaching 0, the average velocity, delta r vector by delta t. Okay, which gives us the differential value, dr vector by dt, the derivative of the displacement vector with respect to time. Okay, so v instantaneous is equal to limit delta t tends to 0, the average velocity vector. which is delta r vector by delta t, which is equal to dr vector by dt. So here the direction of instantaneous velocity, let's say here we have taken the same curved path, okay, between the initial point and the final point. The direction of the instantaneous velocity at any given point is always tangential to that point at that particular point and is always directed in the direction of motion. So here at this point the direction of motion is like this, okay. So tangent drawn at this point, this gives us the direction of instantaneous velocity at point P1. Similarly at point P2 the direction of motion is like this, okay. So tangent drawn at this point, this gives us the direction of instantaneous velocity vector at this point P2. Similarly at point P3 the direction of motion is like this. So if we draw a tangent at this point, this gives us the instantaneous velocity vector direction at point P3, which is along this. So this is the instantaneous velocity vector, okay, its value and its direction. Next is acceleration vector. So we know that acceleration is simply change in velocity by time interval, which we have discussed in one-dimensional motion. So here in motion in a plane or two-dimensional motion, we have to include this with respect to vectors. So the average acceleration vector is simply the average velocity vector, which we have determined below, which we have studied, in the previous thing. So average velocity vector divided by delta t, which is the time interval. So average velocity vector, which we have already specified, which is represented like this, vx I cap plus vy j cap. So again, that is change in the average velocity vector, which is delta vx I cap plus vy j cap by delta t. So that gives us delta vx by delta t I cap plus delta vy by delta t j cap. Again resolved into its individual x and y components. So here delta Vx by delta t I cap, it specifies the change in velocity along the x-axis or the acceleration component along the x-axis. So that is Ax I cap, which is the acceleration along x-axis. Again, acceleration is a vector, so it will obviously have its own individual components resolved along the x and y axis. So this is acceleration along x-axis, which is the change in velocity in this interval, time interval along the x-axis. Again, this specifies the change in velocity along the y-axis in this particular time interval, which is the acceleration along y-axis. Okay, this. So again, acceleration, which is represented as a vector, okay, it can be resolved into its individual components. It is represented as Ax I cap plus Ay j cap. Ax is the x component, Ay is the y component, and the average acceleration value is simply the magnitude of this, root over of ax square plus ay square. Okay, so everything, every parameter in two-dimensional motion, it will always be resolved into its individual x and y components for easier analysis. Okay, then instantaneous acceleration, same as that. Here instantaneous acceleration is same average acceleration with limit delta t approaching 0, shrinking the time interval delta t. So simply it is limit delta t tends to 0, average acceleration vector divided by delta t, which is the time interval, which is equal to dv vector by dt, derivative of the average velocity vector with respect to time. Okay, so here instantaneous acceleration is limit delta t approaching 0, the average acceleration vector. Okay, so this is acceleration, all about acceleration vector, average and instantaneous. Another thing, the direction of the average acceleration vector is always parallel to the change in velocity vector. Okay, change in velocity, not the initial and final, but the change in velocity, that vector. Okay. Next is the relationship between displacement, velocity and acceleration, which we all know. So here if we divide it or resolve it into its individual components, so here first in red we have the x component and in blue we have the y component. So acceleration, which is change in velocity with respect to time or derivative of velocity with respect to time, dv by dt, here as x component is involved, so ax is equal to dvx by dt. Again, vx we know, velocity is change in position or displacement with respect to time, so vx is equal to dx by dt. So when we substitute vx with dx by dt, we have d square x by dt square, second order derivative of displacement with respect to time. Same goes for the y component also. Ay is equal to dvy by dt, velocity along the y-axis or the velocity component along the y-axis. Again, d by dt of dy by dt, where vy is equal to dy by dt. So here we have second order derivative of the displacement along the y-axis or the y component of displacement vector divided by dt. Okay, so these are some of the basic concepts related to two-dimensional motion and motion in a plane, basic introductory concepts. In the upcoming videos, we will be discussing more on two-dimensional motion and motion in a plane. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.